we bother with the humanoid form factor. Um, yeah, I'm super unconvinced personally by the human social side. Sorry. All right, hopefully that will. Yeah, I also don't know why people feel more comfortable when the robot has a face. There's a lot of science to support this. Like the LiDAR head on the digit got axed. Like it used to just have autonomous car style Velodyne LiDAR on top. And yeah, apparently the ones that had sort of like the cartoon like robot heads just test way better with like people's trust and belief. I mean, I get some of it, like things like eye contact and feeling where something is looking is confidence inspiring. But the LiDAR is like looking everywhere. You should be way more inspired in terms of confidence by something with like a 360-degree field of view than something that pretends to have eyes.
I guess it makes it better to like actually deploy it, right? You don't have as much.
Yeah. Yeah, I mean it certainly puts you into like an active sensing problem where you have to decide where to look in order to solve your problem, which is a lot harder. Um, but there's other questions too of like, I think it is not, I think there are very few people who will argue that the humanoid form factor is ideal for any task. Like there's literally no task that if you wanted to solve, you would actually pick a humanoid robot. Um, the argument is that when you want to solve all of the tasks, it becomes the easiest like form factor to choose. Um, but it's really funny when you look at like the demos that have been solved by the humanoid robots, like demos that have been, publicly deployed. I mean, none of them take advantage of the humanoid form factor, really, right? Like the figure one where they just deployed it for how long was it? It was like a week maybe of working like 10 hours a day, I think. Um, it stood at a package sorting station and didn't move. So it didn't need legs for sure. But it didn't even need an upper body it could have just been two manipulator arms, right? The arms didn't need to be connected or look like a human. Um, and then pretty much the same thing, like Figure also had a deployment in a BMW manufacturing line like a long time ago, like a couple of months ago, a year ago, a long time ago in the field of humanoid robotics. Um, and this one, like flat factory floor, wheels definitely could have worked. Like there was no need for legs. It's not stepping over stuff. Um, and then same thing with the upper body. Like there's no reason it needs a head and a face and all this stuff. Um, so the things that everybody points to when they say, "Oh, look, humanoids are useful," are really like not demonstrated yet. There are no good examples, I don't think, of like a robot like carrying a box upstairs or something like that. Or, we have demos of each of these things for sure, but I'm talking about the like large scale deployments. Any of the sort of larger scale deployments are pretty uh, uninspired in terms of like requiring legs. Yeah. Quadrupeds are a bit of a different story, though. Quadrupeds definitely have been deployed in leg-worthy environments. Mostly just like to take a camera places where it's hard to get to, I guess. But yeah. All right. Um, we've already got a couple of people online and a couple of people here, so I guess we can get started. Week 2 of summer. How are we liking it now as opposed to week 1? Nice. Hesitation.
Not hesitation. I don't think I like summer more than yeah.
But you don't know if you like it more or not than what.
Like being able to learn what I want.
Hmm. Yeah. Well, let's get ready to cram a bunch of stuff. Um, okay. So I have way too much stuff up on the board than we're probably going to get through today. I'm sure I was over ambitious, and my notes are just like me writing things down on an iPad, which means they won't be useful, but I'll post them anyway. Uh, everybody got on the Slack if they wanted to be on the Slack. Um, Blake, I can add you to the Slack if you want to be on the Slack. And what was your name? Jordan. Great. Do you have a Slack invitation yet? Or if you wanted one, you can have one. Okay. Yeah. It just you can email me if you want. Cool. Okay. Uh, the Slack is where I'll just like post what the future lecture, or each week I'll try to say what I'm going to talk about. And then there's a Google Drive and YouTube and stuff that are like linked on there that will contain references and other stuff regarding my random thoughts. Okay, last lecture we talked about open problems and like what it means for a problem to be open or solved in the field of autonomy, and how all the different people in the field of autonomy disagree about what this means because they have very different standards for what it means to be solved, and they think about very different problems. Um, and then when I had sort of made some course notes, I had a little section on coding best practices and how to vibe code effectively. And this one didn't get a ton of interest in the initial polling, so we're going to skip it. If people want to talk about how to vibe code or use Git properly or all that stuff, we can talk about it on Slack, but we're not going to dedicate any lectures to it. Um, okay, so we're moving on to the next one, which is again kind of foundational. Uh, in that, not in that much stuff will build off it moving forward, but I just think that as engineers in autonomy, it's important that we know how to think about using tools from simulation to test our ideas and our controllers. So I wanted to kind of get this one out of the way first, and then moving forward, we'll have, uh, I think I have like the series on practical control was what I was going to do next, and we'll talk more about that at the end of this lecture. Okay, but today we're going to talk about simulators and this kind of slow churn from simulators to world models and what world models are. Um, and like I said, we probably have too many data points up here to really talk about, but we'll give it a try. Any questions before we get started? Are people excited to talk about simulators? Okay, that's good, because I was only a little bit excited to give them when I was like starting to design the lecture. I was like, how do I make this interesting and not just me writing down a list of 8 simulators and like the different things they're good and bad at. So we'll see if I did a good job or not. Okay. Question one is, how do we validate anything? Okay, so we are doing something autonomous, like flying a plane or driving a mobile robot around a factory. And we have some sort of problem specification. Maybe the problem specification is get from point A to point B and don't hit stuff, or like deliver all the people and their stuff across the country, or anything else. Doesn't really matter. And we're doing that through some sort of control. We have software that we've written that interacts with the system and with sensors, probably some feedback loops, et cetera. And we now want to validate that that is going to behave in the way that we want it to behave. And question number one is, what does that even mean? Like, what is validation and how do we go about validating something? I will pose this question to you. There are different ways we can think about validating things, a bunch of different standards we can take, but let's just pop some ideas out. What are some like candidate ways we can go about validating that the system behaves how we want? Sure. Do you mean like we try it once? If it gets from point A to point B when we try it the first time, is that validated? Okay, try it, perturb it. This is good. Um, it's not super concrete yet. Uh, let's seed things first. If we asked Aaron Ames how to validate things, what would he say? Okay, we can validate things with theory. So if we have a way to mathematically quantify our problem, we can try to prove that the system we're proposing has the properties that we want. And a reasonable follow-up question is, if we have a proof that the system behaves the way that we want, what have we actually verified? We basically verified that the assumptions we made leads to the correct conclusion. And that says almost nothing about the actual system, right? Because we know that the actual system doesn't obey those assumptions. Um, so we definitely can do this, but we will also need to do extensive hardware testing. Okay, so this was your idea about try it, perturb it. We basically want to take the hardware, put the hardware in every single possible place it could be when we actually deploy the system. Um, and then if we can show that after we fly the controller for 10,000 hours and we have zero failures, the FAA will consider that controller to be certified. And so different industries will have different requirements for how much validation and hardware testing you need to do, how scientific you need to be about that. But in general, really nothing can be deployed without extensive hardware testing. It doesn't matter whether we proved it theoretically or not, because we had to do a bunch of assumptions and stuff here that we know are not going to hold when we go to deploy it on hardware. So unfortunately, that one's not going to be enough. But it would be really nice if there was something that sort of sat in the middle here between these two, right? Like there's other things that are hard to think about theoretically. Like, did I implement my code correctly? Right? The theory says nothing about how good you are as a software engineer. And if you're as good as I am as being a software engineer, you will never implement the code correctly, ever, but definitely not on the first try, right? The first try is going to be like completely wrong, and you'll remove bugs until there's only like 2 or 3 that are left that probably, hopefully don't matter. And if you take that buggy code that has like plus KP times the air instead of minus KP times the air, and you deploy that on the robot, you break it, right? Like if I take the G1 and I flip all the signs of the gains, the robot explodes the first time that I turn it on. And then I have to ask Blake to put it back together again. And this is like, takes time because Blake's not that fast, right? Like No, Blake's very fast. I'm playing around.
Okay.
But point being that we don't want to be breaking hardware the very first time that we turn on our controller that's wrong. And so this is where simulation comes in. Simulation validation has a bunch of great stuff going for it. First off, it's cheap, it's safe, um, and it's fast, right? So we don't have to worry about destroying hardware. We actually don't even need hardware at all in order to run simulation tests. We may need compute, but I'm sort of talking about hardware costs here. We don't have to worry about hurting the hardware or other things in the environment, and we can potentially run tons of simulations way faster than we could ever collect data on hardware. And we don't have to worry about like setting the robot up and putting it on the gantry and carrying it around and everything else. So when we run the simulation validations, we can amass a bunch of hardware experience, or not hardware, we can amass a bunch of simulation experience very quickly. Um, the downside is that, okay, it still doesn't allow us to do this because we still have this gap. I'm going to argue that the gap between the simulator and hardware is hopefully smaller than the gap between theory and hardware. So we've done something, but we still are going to need to run the extensive hardware testing no matter what. But if we validated the thing in sim first, the likelihood that this is going to work the first try or that we're going to be able to do this without destroying the robot or destroying everything else is really, really high. So we can do a lot of iteration if we're doing theory or not. We can do iteration on these two back and forth until we get something that works well in sim, and then we can do the final verification on hardware. Okay, so the sort of key idea here is that simulators manufacture experience. And experience is really the only thing that we can use to validate the performance of pretty much anything. The question with simulators is this experience good or bad? And that's sort of the sim to real gap that we'll talk about in a little bit. Um, this experience is interesting too because it used to be that we would really only use this sort of simulated experience to verify controllers. The modern era, however, has decided that experience is actually all you need to design controllers as well. So for some of this lecture, we also will not just be talking about verification, but also how we can use simulators to generate enough experience to learn controllers and things like this is how RL works. Um, okay, are we clear on sort of the motivation? I think this should hopefully be very straightforward and not surprising, but I just wanted to make sure that we are sort of clear on what it takes to validate something, and then why simulation-based validation is really valuable to have in an engineering stack. Good? Okay. All right. As I often like to do, I have a sort of mental map for a set of trade-offs that we need to think about when we're thinking about how good a simulator is at validating a controller for deployment on hardware. And last time I could break it down nice and clean on two axes. This time we're not so lucky, so we're going to get stuck with a triangle. Okay, but when we're doing simulation, I think there's three kind of critical things that we want to keep in mind. One is fidelity. This is quite simply how good the simulator is at representing reality. Okay. Um, Another one is throughput, which is how much experience we can generate per wall clock time per compute. Right? So Simulators are going to generate experience for us, and they're going to cost time in sort of the literal sense, and they're going to cost compute units, i.e. if I use 10 times as many computers, I can generate 10 times as much experience. But this sort of ratio is a upper limit on how much data we're going to be able to generate or how much experience we're going to be able to generate. And this is unfortunately, a really critical limitation in how simulation scales to sort of harder and more difficult environments. Okay, and then our last one is coverage. And by coverage, I mean effectively how good is the simulator at exposing the system to everything that it will see when we deploy it in reality. And specifically, the question of can the simulator generate long tail, low probability events? And sort of interestingly, I actually want to draw two quick parallels to last lecture. Um, Last lecture, we talked a lot about this uh, structure versus stakes trade-off. And I want to point out that structure is highly related to fidelity. So when we had those problems that were highly structured, we'll note that problems with high structure typically lead to high fidelity simulation, whereas problems that have low structure or no structure typically cannot be simulated with high fidelity, or if they can, they require huge amounts of wall clock time or compute. So structure and fidelity are going to be quite strongly correlated. Um, and then there's also going to be a correlation between stakes and coverage. Right. So we said that when it came to high stakes deployments of autonomous systems, we needed to be really, really robust to these low probability long tail events, like a bird flying into your engine. And systems that are very high stakes are going to require huge amounts of coverage when it comes to validating or even generating data in order to learn from. So the coverage requirements are going to scale very directly with the sort of stakes of the application at hand. And then the structure and fidelity of the problem are going to be quite related when we think about sort of how we simulate different environments. Okay, so I'm putting up a few different axes along which we can think about basically environments and different simulators, and we'll kind of come back to this as we work our way through these various um, points that we're going to make today. And explicitly, we will talk about how typically these things tend to be a trade-off, right? So the idea is that coverage, for instance, often can be generated by cranking the throughput up, right? If I just simulate more and more and more and more, I can sort of get coverage back by like expending a ton of throughput. And then same with fidelity, like lots of times if I want to get a high fidelity sim, I actually oftentimes can, but only at the expense of throughput, right? So if I tank my throughput, I can generate something that's much higher fidelity, but I also am going to get less coverage because I'm not using any throughput. So there's a lot of these relationships here, and we'll think about them in more sort of specific examples soon. But I think those are some kind of critical ideas to be aware of in regards to simulation. Okay, any questions about the sort of super high level breakdown that we've done so far? Yeah. Um, It'll be easier when we start to think about sort of concrete examples. Uh, there will be times when compute can't save us. Like there's nowhere in this triangle that we can be happy, even if we had infinite compute. Uh, but oftentimes we can buy one of these things with more compute and more wall clock time. Um, right? We can't buy throughput with compute because throughput is like per compute unit, right? So doubling my compute doesn't double my throughput, it doubles my experience. Um, Doubling our compute can increase our fidelity for sure, or it can increase our coverage, but it typically can't really do both. Or if you do ask it to do both, it's only going to do either one by a little bit, right? So if instead of my laptop, I use a supercomputer, all of a sudden I can simulate fluids, but I can simulate like one fluid. I can do 10 seconds of fluid sim in the next 3 days if I run it at a really high fidelity, and that's like no coverage. So even when I scale the compute way up, I can normally pick either coverage or fidelity, not both, and then throughput doesn't even scale with my choice of compute. Throughput will, however, scale with fidelity sometimes, right? I can choose like fundamentally different simulation techniques that'll jump my throughput really high, often at the expense of fidelity. Yeah, good question. Yeah,
With the well,
yeah, good question. A problem being considered partially observable, I would argue, is more something that we pay attention to on the controller design side than on the simulation side, right? When it comes to simulating, the world is going to be fully observable, like we control the entire world. Um, we're going to then basically mask out parts of the world and only send certain amounts or certain subsets of the sensor data like to the controller. So from that respect, uh, it's not super clear to me that it sort of plays a role at all here. I will say that one thing that sort of is related to partial observability that does play a big role here is the existence of other agents. So if you are in an environment where there are other agents that are taking their own actions, this is kind of a classic example of a partially observable process because you may not have access to the other agent's strategies or the other agent's states. And specifically, the existence of strategies for other agents can sometimes be very, very difficult to simulate. And so we'll think about how when you're doing things like autonomous driving, where you have other humans on the road, simulating other humans is a job for world models, right? This is no longer a job for sort of our standard simulators because we really don't have good models, sort of in the canonical sense of a model for how humans behave in a car. Um, but we can sort of learn those things sometimes from data, and that's where you get into like neural simulation and world models. No, no, we can definitely have dynamic environments that are still purely simulation based, right? For instance, I could have uh, like a ball that gets thrown in a sim, and the ball is not something that I'm controlling, but it could be something that I'm dodging. And the ball has a very good model behind it. It's something that's certainly dynamic, but it's highly structured. It's easy to simulate with high fidelity. Um, so I would consider that very different, and that's certainly something that I can simulate. We'll talk about world models in a bit, but when I say world model, I'm specifically referring to things that typically generate sensor data or video directly from a prompt or like a data log. So there are autonomous driving world models that will basically take all of the data logs from a car up to a certain point and then a text prompt, and they will then simulate forward the future like sensor data for the autonomous car, right? And this is a purely neural, often diffusion-based process that's not actually grounded in physics at all. It's only grounded in sort of data collected. Um, and we'll talk about how you know, a world model still fits into these trade-offs. It will typically have some of the best coverage when you're trying to deal with those low probability events because you can ask for them in text. But its fidelity will be, depends, right? If you're super in distribution, the fidelity is probably okay. If you get out of distribution, it's horrible. And then the throughput is, kind of as bad as anything else. You might need a stack of GPUs to inference, even one of these things. Okay. Any other questions on the sort of trade-off architecture? Okay. I'll go ahead and tick off these first two items. All right. Before we dive too deep into any uh, more philosophical bents, I wanted to just take a quick second. I don't want to spend too long on this because it's not the most interesting thing, but I am going to kind of just write down a list of simulators that I think you should be familiar with um, as a roboticist, and then maybe just as a like autonomy engineer. And in order to make this not a boring list, I'm just going to note that simulators are worldviews. Right. And so when I choose a simulator, I'm implicitly making this choice about what portions of the physics of the world are the ones that are important for the problem that I'm solving. And this means that there are like good and bad choices of simulators for different application domains. Um, I'll start with some that are just the robotics, because this is the field that I'm obviously most familiar with. We have Mujoko. Um, Mujoko is very good at rigid body dynamics. And it is a fast CPU sim. I'm going to note here that MJX, whoa, is a very new GPU-based variant, and we'll talk about why GPU-based variants are important in a bit. Another important mention is Drake. Drake is a brainchild of Russ Tedrick out at MIT, and Drake is perhaps most well known for the hydroelastic contact. So it will be a slower simulator, but it has much, much higher fidelity contact modeling, especially for deformable bodies, patch contacts, these sorts of things. So for people who are doing um, manipulation work or highly dexterous manipulation, if they want a policy that's or a simulator that does a better job representing reality than Mujoko, they often will go to Drake. Um, and then sort of on the other end of the spectrum, we have Isaac Sim, which is GPU based, cheap, low fidelity. And the idea here is that this is a simulator that explicitly is trading fidelity for throughput. So it's going to also pretty much only be good at rigid body dynamics. It's going to struggle with complicated contacts potentially and all of these sorts of things, but it's GPU parallelized and it's going to have more throughput than basically any other simulator on the market. So it's very good at generating data. The data may be low quality, it may not be low quality, and you might care or you may not care, depending on really whether your system is high stakes and you may or may not need high fidelity sim. Um, these are, I would say, the three most common simulators in robotics. We also have Gazebo and PyBullet and a bunch of other ones, which get some use. But I think these are the ones that I find it most important to know. And then I was just going to write down a couple other ones that are sort of outside my personal domain. Carla is a open source autonomous driving sim, right? And so notably, this is a simulator, not a world model, so it does simulate real physics. And it will also simulate pedestrians and other vehicles and things like this. So they will have pedestrians that are sort of solving navigation problems using A star and then like walking on A star paths like around their environment with some probability of crossing the street in random places and things like this. And then similarly, they have rule-based driving for all the other cars on the road. So they're attempting to sort of cover a large swath of the problems in autonomous driving, but because all of their agents are following controllers, which are not the controllers that real agents do, there's necessarily going to be sort of this, at least this long tail gap where you're not going to get the sort of crazy behaviors that you'll see if you drive enough, say, in Los Angeles. Um, and then There's also really good simulators, obviously, for the aerospace environment to simulate planes and aerodynamics and all these sorts of things. So if you're doing autonomous flight, you should be aware of these. There's also like just Air Sim from Microsoft, which is pretty good for sort of the high level stuff of autonomous flight. Um, okay, we've set down a list, and the point of this list is really for me to just say like, okay, here's three different simulators. They all are super different. And so if you are walking up to a problem fresh, you should not be grabbing one of these simulators at random. There's like a strong case that only one of these is going to be right for your problem. Um, and it might be that actually your problem may even want more than one of them. For instance, I tend to use Isaac Sim to train the RL policy and then Mujoko to do my simulation-based verification, right? And the reason is because here to train the RL, I need the high throughput. People also use MJX for this as well, which again is not actually as high fidelity as Mujoko. Um, but then when I'm trying to verify that the policy actually works, I don't need the throughput as high anymore. And so I can go down to Mujoko for the increased fidelity to help get the sim to real transfer. So different parts of the same pipeline may still even want different simulators, even though it takes a little bit more software development to set that up. Okay, points made about there exists a right and a wrong simulator for each problem. Let's have somebody propose a problem that they're working on and think about what simulator would be best for it. Yeah.
Stuff with different making models do that.
Yeah. Okay, cool. So we have like elasticity implies deformable bodies. So we have deformable fingers that are picking up different sorts of things. Okay. What simulator are you using now, or do you have one? No. Okay. And that's fine. I mean, especially if you're doing things that are low stakes and hard to model, a lot of people just prefer to use the real world as their simulator instead. And we'll talk about why there's advantages to this. Um, if you did want to go to a simulator, well, Isaac Sim would be a horrible choice because depending on what you're doing, you might not really care about throughput. And Isaac Sim doesn't have good tools to support things like deformable bodies. Uh, Mujoko might be okay. That's probably what most people would use just because it has more widespread support. But especially for like deformable bodies and patch contacts, Drake is often like a really good choice to get high quality results from the simulation. So, um, anybody else want to propose a problem? Okay. Trajectory optimization for M4. So M4 is a hybrid ground air vehicle, right? Um, if you're doing trajectory optimization, you probably don't need the same amount of throughput that you would for like RL or something like that. So you probably don't need a GPU-based sim. Uh, and so that probably will leave Majoko as like a good default. Um, a lot of people use for drones specifically might lean Gazebo because Gazebo has built-in support for PX4 and like some of the flight controllers that fly on drones. Maybe that should have gotten up on this list for exactly that reason. So Gazebo could be a good choice as well, particularly because the contact is so simple. The sort of rolling contact isn't particularly challenging to model, so you might not need the fidelity that Majoko has. Okay, so everybody will do their own research and pick their own simulator. Yeah,
These fidelity and well, Drake would be the highest fidelity that than Isaac Sim, and then the throughput would be reversed basically.
exactly correct. Yep, exactly correct. Yeah, Isaac Sim has the lowest fidelity and the highest throughput. Drake has the highest fidelity and the lowest throughput. And then the coverage of each simulator depends on the application. So I can't, you can kind of analyze those two axes just based on the simulator, but coverage is like a super application dependent axis. So for me walking my bipedal robot around a static environment, the coverage of Isaac is actually like pretty good. Um, But if I was trying to pick things up, then the coverage of Isaac would actually, maybe not be good enough. Good point. Okay. Uh, I am now going to take a second to talk about, I think we'll actually talk about GPUs next. Okay. How many of us are like already familiar with the details of GPU-based simulation? No? Okay. All right. That's good. I don't feel like I'm talking about it for no reason. Um, so when we started doing reinforcement learning, it started to become sort of more important than ever before to be able to generate massive amounts of data very quickly. And it turns out that the GPU, in some cases, is an excellent tool for this. And I just wanted to talk a little bit about why. So the CPU is a single thread fast processor, right? So it's going to take in basically serial operations that it will perform one after the other, right? So it's going to basically do one operation and then move to the second operation and then to the third operation. And the GPU is sort of fundamentally different. It contains many logical processors, which can spawn processes in parallel. And specifically, in order to do that parallel spawn, it needs things to satisfy this process called single instruction multiple data, or that's SIMD is an abbreviation that you will see. And how single instruction multiple data works is that the entire GPU basically will be running only one instruction at a time, and it will be doing so on many, many, many data all at once. So I'm going to use here just matrix multiplication as an example. In general, instructions cannot be sort of arbitrarily complex. When I say instruction, I mean like an atomic instruction, something like multiplication, addition, um, and sort of the atomic ways that those can be combined, which ends up covering linear algebra mostly. So if we can think about these instructions as being linear algebra instructions. And so I'm going to use the matrix multiplication as an example. If we have a matrix multiplication that looks like this, and we'll say that, I'll just say for simplicity that A and B are in R n by n. And I want to look at the ith row, jth column of the resulting matrix C. How do I compute that? Right? So we're just taking I've written it with this transpose so that we can just say, okay, it's the ith column of A transpose times the bth column or the jth column of B. Okay, so this is just an inner product. And notably, this inner product doesn't affect any of the other entries of the matrix C, right? If I want to determine one of the matrix or one of the entries of C, I need to look at exactly one row and exactly one column of the big matrix. And so that also means that I could do these in any order, right? If I want to compute all of the entries in C, I don't need to start in the top left and like work my way over the first row and then down, I can literally pick any order or a random order. And on a CPU, this is actually effectively what's going to happen, right? If I lock a matrix multiplication to a single thread, it's going to compute the first element of C, the second element of C. It might not even happen in order, but it's going to compute them sort of one after the other. So the CPU is going to compute, C11, and then it's going to compute C12, and so on. However, each of these computations is actually doing the same logical instruction, right? It is a inner product on two vectors where the vectors get grabbed from the matrix A and B based on the element. So I could write this as like an atomic operation as an inner product and two indices, right? And then my sort of atomic operations would be go grab the ith column of A, put that in this spot in the inner product, the bth column of J, put that at that spot in the inner product, take the inner product, and then assign it to the specific cell in the resulting matrix. And if I define that process as like an individual logical process, I can then spawn that on all of the GPU like processors all at once, and the entire matrix can basically get multiplied in a single process in parallel rather than happening sequentially one after the other. So when we do this on GPU, what's going to happen is it's going to spawn processes all at once. They'll aggregate into C, and this entire matrix multiplication will happen in one step. So to put that in perspective, if we say that n is equal to like 4096, which is a fun number that comes up a lot in reinforcement learning, I wrote down a couple of numbers that then the matrix C is going to have 16.7 million elements. And this operation is going to use 137 gigaflops. So that's floating point operations per, or not per second, just floating point operations. And this is just a measure of like how many floating multiplies I need to run and additions. And if I run that on a single thread CPU, it'll take about 1 second. So if I take those two big matrices and I try to multiply them on a CPU, it'll actually take like a fairly long amount of time. If I multi-thread the CPU, I can get this done in 0.1 seconds, and linear algebra backends on CPUs will multi-thread stuff. So they'll take care of a lot of that sort of overhead for you and do this more efficiently. But if I do it on a GPU, we can see this operation happen in about a millisecond. And the sort of general rule of thumb is that the GPUs actually are going to be slower than the CPUs when it comes to each individual instruction that they execute, maybe even like a factor of 10 times slower. But they can execute so many of those instructions in parallel that you're going to get a 100 to 1,000 times increase in the throughput. Yeah. Yeah, so if you get like a Threadripper from AMD, which is sort of a top of the line multi-threading CPU, those will come with like 96 threads. A GPU is going to come with thousands of tensor cores. So like the biggest, baddest CPUs that we get are going to have fewer threads than the weakest GPUs. So we are dealing with a difference in scale. So there's definitely going to be more threads. That being said, there's much stronger limitations based on this single input single instruction, multiple data architecture, right? So I can write code that executes on a CPU that just doesn't execute on a GPU. A really good example of this is an if statement. The if statement, if I write if x greater than 0, do this to x, otherwise do something different to x, that actually is not an example of an instruction that follows this paradigm. And it's because there's this branch that actually has me doing different operations to x depending on what its value is. And that's no longer a single instruction. So backends like PyTorch are going to do a lot of work to allow you to write things that look like if statements or even write if statements. And basically, they will optimize the if statements out of the code. If you're trying to write efficient code that runs on a GPU, it's actually really important to understand these sorts of behaviors. Because if you are in Torch and you're writing a bunch of if statements, your code is going to execute much slower than if you are using the appropriate like torch.where calls and avoiding branching in the sort of torch-centric portions of the code anyway. So if you're not familiar with single instruction, multiple data coding, and you're like taking on a project that is going to have you interacting with a GPU a lot, I would spend a little bit of time looking at this. And you can look at, for instance, libraries like JAX are good because they are super explicit about this. If you look at JAX, JAX won't let you write an if statement. It won't even let you write a for loop. Like you have to use sort of custom instructions that replace if statements and replace for loops to make them fit this single instruction multiple data paradigm. So if you're new to this, go write like an example program in JAX and you'll get a bunch of understanding about how this works and what you need to do in order to make code compile efficiently for a GPU. Yep. So you can totally do this. The problem is that the CPU and the GPU have different memory. The CPU is accessing RAM, the GPU is accessing VRAM. So if you want to switch data from the CPU to the GPU, you have to copy stuff over from the GPU or from the RAM to the VRAM. This copy operation typically will take longer than all the instructions would have anyway. So to go from the CPU and GPU and back is almost always sufficiently slow that it kills whatever benefit you would have gotten from the GPU anyway. Um, Absolutely. If you have the unified memory, you can get around this. And so Jetsons have unified memory. New Apple chips have unified memory. And this allows you a lot of flexibility, but also a lot of the programming languages aren't designed for that yet, right? So if you're just writing Python code, uh, writing like matrix.2 CPU and matrix.2 GPU are not necessarily going to be intelligent operations that are going to take advantage of the unified memory like structure. So if you're in an environment where you have unified memory to take advantage of, you need to make sure that you know how to properly like program and adjust for it because it's not free. Yeah. Okay. I now want to think about what this means in the context of simulation. Uh, Trying to think about how to pose this question in an approachable way. Um, let's do rigid body simulation first. If I am simulating rigid body dynamics, what does that simulation come down to at its core? So you got translation, rotation matrices, what are you going to say? F equals ma. Okay. F equals ma is I think good. We need to couple that with like some rotations and and translations to get, maybe the Euler-Lagrange equations or whatever. But at the bottom line, they're going to end up looking like F equals ma with like some extra steps. What is F equals ma? What kind of equation is that? Sure. Um, a vector valued what? Uh, There we go. Rigid body dynamics is us solving an ODE. Okay, now let's think about the steps required to solve an ODE. How do I solve an ODE? It's integration, right? At the end of the day, rigid body dynamics is solving an integral. Now, integration is a great example of something that obeys this paradigm really, really well, right? If I have, say, like the manipulator equations, then solving this integral basically boils down to evaluating D, evaluating H. The input U is going to be given to me. And then all that I then have to do is like integrate forward the Q, right? And so if D and H are things that I have analytically, right? Like I have solved the Featherstone equations or something that will give me explicit algorithms for computing D and H. The only thing that's sort of left is for me to take an Euler step on Q double dot. And all of those instructions are things that don't have any branching. I can apply literally the same algorithm independently to all the different robots in my environment. And so when we think about this GPU-based stepping, I can have environments with thousands of robots where I just apply the same forward step of the dynamics to every robot all in parallel. So rigid body dynamics is a good example of something specifically solving ODEs that follows this single instruction, multiple data paradigm very, very well. However, what happens if we introduce, say, even contact into the mix? What happens if I want to simulate a rigid body with contact? How does that change my, like, okay, I just said rigid body was just integrating an ODE. How does that class of problem change? Is that a question for me? Okay. Does anybody else want to think? How do we tend to model contact? Yeah, right. Okay, so Sean, how do I model contact is like an era-defining question. There are a lot of ways to model contact that fall everywhere on this fidelity throughput coverage spectrum. So I can't give you one answer. If I am doing rigid body dynamics, we typically model contact via, you have to first detect when contact happens. Once contact happens, you then have to determine whether that contact is a sliding contact or a pinned contact. Once you make the determination whether it's sliding or pinned, you then will apply the appropriate constraint onto the system, and then you will solve a constrained ODE. The problem is there was a lot of branching in there. And when I have, let's say I have 4,000 environments running all at once, they're not all going to be in the same contact configuration. And as soon as they're in different contact configurations, I'm now applying like different dynamics to each one, right? I have this if statement that's determining which contact they're in. So contact sort of naively does not follow this sort of single instruction, multiple data approach at all. And most simulators are built to handle contact. And this is why GPU-based simulation didn't take off like when GPUs were invented. So it took some very clever people to think hard about how to approximate contact in a way that satisfied this single instruction, multiple data paradigm before GPU-based simulation really took off. And it was literally when GPU-based simulation took off that RL exploded. So it's not like reinforcement learning didn't exist before GPU sim did. It did. There were people who were running RL on CPUs. Um, but nobody tried running RL on a CPU for like 3 months, right? Nobody was like, this problem, I know what's going to solve this problem. I just need to compute for way longer. That wasn't really how people used to think. Now we run RL problems for 3 months on a GPU, which is, again, 100x throughput difference. That's 300 months on a CPU, right? So they were like so far away from the invention of this GPU-based simulation from unlocking the throughput scale necessary to do reinforcement learning that it was really a discovery and a method that was unlocked by figuring out how to do simulation within this paradigm. So Isaac Jim was basically one of the first, which gave way to Isaac Sim, Brax, MJX. I mean, now there's a ton of GPU-based simulators, but all GPU-based simulators are basically going to fudge around those contact equations to find good approximations of them, such that we reduce fidelity a bit. So fidelity is going to come down, but we're going to jump throughput massively because we're leveraging a fundamentally different paradigm of compute. And then once we have all that extra compute, all that extra throughput, it allows us to do completely new things that we couldn't do before, a la reinforcement learning, domain randomization, all these other things. Yeah.
Oh, and like, launching SIM anyway, and then those are decided, like, what is that?
Yeah. So I have on the Google Drive, I have like a list of papers for this lecture linked already. One of those papers is learning to walk in minutes using massively parallel reinforcement learning. That paper was the paper that sort of first came out, like that really kicked off the field of RL. And this was based on the simulator called Isaac Jim. That paper will cite the original Isaac Jim paper, which I think is probably the first place to look at for these sorts of things. I will write down the names of some of the simulators. Each of these simulators will have a paper, and I can put them in the Google Drive later as well. But I would look at Isaac Jim. This was sort of the first one. We now have Isaac Sim. There's Brax, and there's MJX. They all do things differently, but they all are doing work to basically handle the contact in a way that vectorizes over GPU well.
And, yeah, say that the reason contact manipulation progressing as quickly and like fluid motion, for example, is because the assumptions that you're making in order to like run it on GPUs, or it's hard to get like few contact models that run on GPUs basically.
Yeah, I think that a lot of people think this. I do not maybe share that belief. Um, I think there is no doubt that Drake will outperform every GPU-based simulator by a mile in terms of the contact fidelity. Uh, so the answer is yes, you are certainly limited in terms of the accuracy that you can get out of the simulator in order to perform manipulation tasks. I think a lot of people take that, which I think is a fact, and conflate that with a cause. Um, there have recently been papers that are showing that you actually can get reasonably decent manipulation policies applying the same RL techniques. The problem may actually lie somewhere else that is not the RL algorithm or the data generation algorithm. There's a few places, one of which is that manipulation, I think, is actually a lot more complicated than walking. If we say that contact is like the limiting factor, walking has two really simple contacts. So even though I can't, model them that well, there's only two of them. Whereas manipulation has like a ton of contacts. And it actually might not be that we can't model the contacts well enough. It's that the contacts complexify the problem to a point where standard RL methods like just actually maybe don't scale. And this is where we see learning from demonstration and these other techniques taking off, is because they don't try to solve the problem via random search. They actually query a human to solve the problem first, and then they just try to learn from the solution, right? And so all these learning from demonstration basically says like, look, the manipulation problem is just too hard. Nobody knows how to solve it except for us. We can't express why mathematically, but we can sort of do it. So just film somebody do it and copy that. And a reason that that works might not actually be the contact modeling as much as it's the problem complexity. There's another problem that's hidden in here, which is for RL-based methods to work, you need good estimates of two things that you don't have, which is the geometry and inertial properties of the object you're trying to manipulate, and the pose or dynamic properties of that object while you are doing the manipulation. Um, so we're really good at estimating the like dynamic properties and pose of the robotic arm because we're in control of all of the joints. You can measure them. Uh, this is not true of an object you're trying to manipulate. Like if you're grabbing something, one question is how do you even know the like shape of the thing that you're grabbing? And if you do know the shape really well, actually RL tends to work a lot better. So if people do RL on the specific object you're trying to manipulate, your success is going to go up. But people aren't really trying to solve that problem anymore because if you already know the object geometry, you can just pre-plan stuff ahead of time using more classical methods. And like this actually probably works reasonably well. They're more concerned with how do I manipulate anything? And if I manipulate anything, then I can't assume I know the geometry ahead of time. I have to be able to estimate the geometry based on a LiDAR scan, a camera image, etc. And these problems are like definitely not solved. Blake just was talking today about a paper that used SAM 3D to like extract meshes from objects and then foundation pose to like estimate the pose of those objects online. And both of these tools are very new. They're rough around the edges, and those things can also be limiting factors that present obstacles to progress in manipulation. Is like, how do I identify what I'm picking up and where it is in order to feed that back to the reinforcement learning policy? Because if I don't have the pose of the object I'm trying to manipulate, it gets like really hard to manipulate it. Um, The other option would be to condition your manipulation policy directly on like an image, and now you're stuck in photorealistic sim realm. That kills your throughput because simulating images is slow. So there's like a big space of options here, and I think it is not accurate to say that contact modeling is like the only thing that's holding back the manipulation front. It might be one, but there's like a lot of other ones. Yeah. Okay. Uh, this lecture is trying to do a lot of stuff quickly, so I'm not like trying to have made you a GPU expert here, but I am trying to expose you to really this keyword of single instruction, multiple data, so that when you are trying to implement things on GPU in the future, you're aware of this. Maybe you sort of have a rough idea how it applies to the matrix multiplication case, and then you have sort of the historical background of how GPU sim came about, the class of tools that it unlocked, and why it's like really popular now. Do we think we hit those like steps here? Okay. All right. Next thing I want to talk about is sort of a bit of an engineering bent. Okay. A digital twin is a term that like NVIDIA coined at some point, I think, that refers to a simulation environment that sort of exactly mirrors reality. And of course, this doesn't exist. But the idea of a digital twin is sort of the like critical idea that we're aiming for when we think about verifying things in simulation in general, right? We want an environment that mirrors reality so closely that when we verify that it works in sim, it'll transfer to reality with sort of no loss. And while one component of like designing digital twins is certainly the fidelity, throughput, and coverage of the associated simulator, another part of it is actually software design. Oftentimes, people will maintain two completely separate stacks for their control code, one that interacts with like the simulator and a different one that interacts with the hardware. And I wanted to propose for a second that when we're doing simulation-based validation, we actually want to run the exact same code on, against the simulator and against the hardware. And the way that we do this is, we have some control code that is going to have like some inputs and some outputs, right? So maybe this is like sensor data coming in, and these are like actions going out. And what most people do is when they hook up to a simulator, the sensor data comes out of the simulator looking some way, and the actions need to go into the simulator looking some way. And so they just kind of like toss the simulator right next to it. They say, okay, look, this is my simulator. And then when they go to the actual hardware, the hardware looks different. And the way that it has inputs and outputs is not the same. And the way that they rectify that is by taking this control code and like making a copy of it and then interfacing this new copy with the hardware. And this is a bad idea. The reason being that ideally you would want those two pieces to be the same. So what I'm just saying you should try to aim for instead is what we like to do is you should write an interface where the interface talks to the simulator. And then you have another interface, and that interface talks with the hardware. Okay, so you have to design these two interfaces up front, but the idea is the job of this interface is to make the simulator and the hardware sort of mechanically the same from the software perspective. So if you're using ROS, I should have the same ROS messages, for instance, that pass to my simulator and pass from my simulator as I do on hardware. And if you've done this construction properly, then it literally should be, you shouldn't even need a flag. Like if this has been done sort of at the best level, the control code you boot up, and then either the robot is already running, in which case the control code starts talking to the robot, or the simulator is already running, in which case the control code starts talking to the simulator. But the control code is going to treat those two as exactly the same object, right? They are like not different. And I'll say it's not always possible to do this completely, but this is sort of the idealistic world that we should aim for. And the reason is that then this piece of control code itself is what's getting validated. Because again, we want to be validating not only the approach, but also like our implementation of it. So we need to know if our communication protocols are robust, if we've written bugs, these sorts of things. And if you're maintaining two separate stacks of your control code, one which deploys on hardware and one which deploys in sim, then the sim validation actually means nothing because you haven't validated the other piece of code that you're actually running on the hardware. So again, this idea might be obvious, or maybe you even think it's unnecessary. All that I'm going to argue is that I think if you are in, for instance, the aerospace industry, this is going to be the standard, right? Boeing does not maintain a sim stack for their flight controller and a hardware stack for their flight controller. They maintain a flight controller, they run it in sim, they even run it hardware in the loop, meaning they run the flight controller on the computers in the plane and then pipe in the simulated sensor data like into the plane so that they're running it on the same physical hardware that it will run on later. So the better that you can align like these sim and hardware interfaces and make it so that your control code is the same when it's interacting with these multiple environments, it will really help you reduce the sim to real gap, and it should allow you to iterate much more quickly and have things transfer to hardware sort of better and quicker. So kind of an engineering ideology that I just wanted to mention. Any questions on that ideology? Okay, we're getting through it. We're making good progress. The next thing that I wanted to talk about is sort of limits of simulation. And I wanted to identify sort of two different classes of limits. The first class is fidelity limits. So when I say fidelity limit, I'm talking about something that we sort of can simulate, but maybe we can't simulate accurately. Um, and there are sort of many examples of this. We have things like slip-stick contact. Right, so I said this, I sort of alluded to this already before, but if we know ahead of time that the contact is not going to move, this is like reasonably easy to simulate. But if the contact is going to like move and then stop moving, right, like, you know, something like that, where I am like moving, sliding, but then at some point the thing is going to stop, or a canonical example is something like the remote sliding. Me figuring out like where and how that thing is going to stop is actually a really, really hard problem. Um, a canonically hard problem for simulators to do is something like a box being pushed on the edge, because sort of exactly where the force is applied will determine if the box rotates like to the right or to the left. Um, all of these sorts of like slip stick or very fragile friction dynamics are quite difficult to simulate. We also have deformable bodies, granular media. So things like sand, rocks, gravel, um, fluids, including air, aerodynamics, and then photorealism. So things like cameras, images. All of these things are going to present potentially very, very high limits on fidelity. And the interesting thing with these fidelity limits is that we can often trade throughput for fidelity. Um, you'll never maybe achieve 100% accuracy, but typically there is some gradient here where you can always buy a little bit more fidelity if you expend maybe even a lot more compute, right? It's not necessarily like linear scaling. Um, but if we think about, say, deformable bodies, if we just start running FEA, we can get with, some amount of finite elements, we can get some amount of accuracy. And in general, if we just keep cranking the number of finite elements, we can get things that are more and more accurate. But as we scale the finite elements, um, both our compute and our wall clock time are going to explode in order to get the same amount of experience. So with these fidelity limits, we actually often can make progress on them, but we have to expend compute at the sacrifice of throughput. And when we sacrifice throughput, it often will take the simulator from the realm of usefulness into not being useful, right? If I need a supercomputer to simulate my foot dynamics when I'm training my RL policy to walk, it's not going to be useful because I need to simulate 1 million hours of robot experience, and each minute of robot experience takes me an hour to simulate. And so that sort of just doesn't scale. That policy won't finish training while I'm alive. So these limits, even while I can maybe simulate each one of them well enough if I crank the compute, still are going to provide super fundamental like limits on their usefulness depending on what we're trying to apply the simulation to. Um, the other class of limits on simulation is even worse, uh, which is things that we sort of are unmodelable. And of course, the learning people might argue with my statement about unmodelable, but I'm going to say unmodelable from physics principles. And these are things like, say, human decisions. So if I have a simulator that I'm trying to validate an autonomous car driving in, one of the major limitations is it's going to be very hard for me to capture the behavior of humans inside that simulator. Um, we have things like other agents in here, or even like unknown physical phenomenon. So if you're somebody who's doing control of a fusion reactor, your actually primary limitation might sort of not be a fidelity limit as much as it is that we actually don't understand some of the quantum effects like well enough to actually simulate um, them at all. So we cannot make progress by just trading compute. There's actually sort of a unmodelable dynamics that we don't understand. So for the fidelity limits, I'm going to make this argument that we can trade throughput for fidelity by spending money on compute. For the unmodelable physics, we don't even have that option. And so our alternative approach um, is to head sort of back into data land. And this is sort of where world models are born. Um, if we are having a really hard time modeling the physics, an alternative approach is to collect a bunch of data from the real world and then use that real world data to train a neural network that's going to effectively replace our simulator. And so we'll talk more about world models in a bit, but I just wanted to note that, okay, we have two classes of limitations. One class is limits on the fidelity of the simulation, and we can approach this by trading throughput for fidelity. And the other one is that the certain elements of what we need in order to validate might just not be modelable. And the only approach that we really have here is to turn back to data. If we can't model something, we need to collect data of it happening, and then potentially we can learn a model of it sort of from that data. And we'll talk a little bit more about world models in a second, but um, yeah. Yes. Yeah, they certainly can. There are people who work on this. They have not found great purchase as of yet. Um, Part of the problem, this is a great question. Part of the problem with contact modeling is that it is quite difficult to collect data. Um, Most world models uh, work basically the same way that video generation models do. So they are going to effectively just generate a video of the physics that you want to simulate. And so if you're trying to back out like the pose of the object or the trajectory that the object takes, world models actually often won't give you that. World models are typically going to say there's actually a camera in the scene. I'm going to skip all the physics and just do the rendering. And so if that's what you care about, then sure, you can use that approach to like model contact as well. Um, but then the world model needs to be trained on a bunch of wacky contact situations, right? And this is hard. We just don't have like a lot of readily available video that covers the space of hard to model contacts. Whereas if you train the world model sort of on like all of YouTube, it might not be great at modeling contacts, but it'll be like reasonably good at modeling most things. Um, but yeah, the world model approach is less of like, can I predict trajectories and predict things from states, and more, can I just directly predict the outputs of sensors from internet scale training data? Okay. The other way, the video is the sensor output. The sensor that they're simulating is a camera. So like the canonical world model that, Cosmos from NVIDIA is basically a diffusion policy that's going to take in like a prompt and generate a video. Um, and then, yeah, people will use these things for control, where they'll even like they'll say, okay, in addition to predicting the next frame, now also predict the action that the robot needs to take to like get to the next frame. And there are people who, but this is like one of the ways forward, like one of the most cutting edge techniques for robotics is to just like append an action to the video frame that a world model is sort of predicting forward, which we can talk more about in later lectures. But yeah, sort of directly predicting the sensor data, where the sensor data often is something like an image. Okay, so we had two limits of simulation. Uh, all right, and these limits will then lead to a verification gap. So because we can't simulate the world perfectly, and nominally we can't simulate the world perfectly because of one of these two limits, we end up with a verification gap where we've verified something in sim. That doesn't mean that it's verified at all on hardware. And so the question is basically, when I have a policy verified in sim, and it fails on hardware, well, sort of now, what do you do? And this is what's known as the sim to real gap. And of course, it can sort of look different in every particular instance. Um, but the sources of the sim to real gap typically are going to fall into either dynamics, i.e. you haven't modeled your dynamics well enough, perception, uh, or sort of long tail events. So dynamics are really easy to break down. This is like my friction model is bad or my contact model is bad. Perception is a big blocker for things like video, right? If I am trying to condition my policy on the output of a camera, I just can't simulate the camera perception well enough for that to be useful. And then long tail is more like my simulator never put a goose in the plane engine, and so I didn't actually encounter that particular um, behavior in sim. Uh, and each of these sort of has their own set of approaches. Uh, for dynamics and perception, the two dominant approaches are domain randomization. So domain randomization is where I take the physical parameters of my robot and I randomize them, or of my camera model or anything else. And what you're doing here is you're exchanging fidelity for coverage. So the idea is that, like, let's say I'm training an RL policy, it works fine in sim, doesn't work on hardware. The reason for that is because the simulator is not giving me enough coverage of the states that I'm going to see on hardware. And one of the ways to increase my coverage is actually to make the simulator worse. Rather than simulating exactly what the robot's going to do, I'm going to put a bunch of noise around that, and that's going to make my policy visit a bunch of new states that it needs to learn how to be able to control for. So I can reduce the fidelity of my simulator, bump the coverage up, and in doing so, make sure that my policy is sort of more robust. Um, the other approach is called real to sim, which is sort of the other way. And this is like exchange effort for fidelity. So in real to sim, I'm going to go collect a bunch of data about how my system actually moves. And then I'm going to use that data to fit the simulator better to reality. And I can do that through sort of standard system identification, where I just make sure that my parameters are right. Or I could learn residuals, right? There's like actuator net or all these things where people will basically learn the internal dynamics of a motor or something like this, and then append that into the simulator so that the simulator more closely mirrors reality. So when I have a failure that is due to the dynamics or the perception, I can either domain randomize, which lowers fidelity to up the coverage, or I can do real to sim, where I take a bunch of effort that I do in data collection and like pre-processing, and then use that to improve the fidelity of the simulator. Um, Now, notably, neither of these deal with the long tail events. Um, Long tail events are really hard to deal with, and this is what's leading us back to sort of the world models. Whoa. Um, the only way to handle long tail events is sort of to simulate them, and you can't really simulate them if you don't know that they're coming. Um, you can maybe sort of treat this problem with real to sim, right? If I see a long tail event happen, I could then be like, oh, I'm going to simulate that. And then you could try to put exactly that long tail event back into the simulator and make sure that you're robust to it. But this is a pretty hard process to do. Um, The alternative approach is basically to just try to start training something that's going to um, sort of inherently give you, or that you can even request long tail events from directly. And I just will make two quick notes. We have a neural reconstruction, and we have generative world models. Both of these have links in the Google Drive that you can go to look at the some specific examples. Um, but neural reconstruction is a particular method that falls under world modeling a bit, where you take maybe something like a bunch of camera images of a room and you generate a neural reconstruction of that room that allows you to render new camera images from sort of any location. And this is as opposed to another approach, like if I wanted to generate camera images from arbitrary angles in this room, I could also try to model the entire room in like Blender or something, and then render images sort of from the model. The alternative approach is I could just take pictures from the room, generate something like a 3D Gaussian splat model, and then use that model to render new camera images from sort of different locations. So the neural reconstruction will like use data to generate an intermediate representation that can then be rendered. And then the generative world modeling is sort of what we said. I'm going to do like next token prediction on video, condition that on a prompt or something, and now you can ask your simulator to sort of produce anything. And a really good example of these general world models that I would advise looking up is the Waymo world model. They have a cool little blog post on it where they like will ask you to, they'll ask it to put an elephant in the middle of the road, and that